Hi all, welcome back to electric potential part 3, and it's about equipotential surfaces for an isolated charge. The electric potential can be represented for positive or negative isolated charge graphically by drawing equipotential lines or in 3 dimensions equipotential surfaces. The dashed lines represent the equipotential surface. What is meant by an equipotential surface? An equipotential is a surface on which the electric potential is the same everywhere. So for point A and point B, they are on the same equipotential surface. So the electric potential for VA equals to VB and not equals to VC because C lies on different equipotential surface. So work done from B to A, so here should be B to A. Sorry for the break, typing error. And we can see point A and B on the same equipotential surface. They have the same electric potential, which is VA equals to VB. Therefore, VA minus VB is 0. So work done B to A is 0 or 0 joule. How about equipotential surface for a uniform electric field between two parallel plates? So the dashed lines represent the equipotential surface. Point A and point B have same electric potential, where VA equals to VB, which is not equals to VC because C lies on different equipotential surface. To find the work done from B to A, work done B to A equals to Q times V. Again the error occur, typing error, sorry for the break. B to A, the change of the V is 0, so the work done B to A is 0 or 0 joule. These are the 3 important points for equipotential lines and surfaces. The first point is about an equipotential line is a line on which all points are at the same potential, followed by no work is done when a charge moves from one point on an equipotential surface to another point on the same surface. It is because the potential difference is 0. And finally, an equipotential surface must be perpendicular to the electric field at any point. Let us try to attempt PSPM 2 2008-2009 quiz number 10. Figure 5 represents the equipotential surfaces and electric field lines near a positive point charge Q. A. From figure 5, give 3 relationships between the equipotential surfaces and the electric field lines. You have 2 options to answer section A. The first option is you can explain these 3 points which I already explained before, or you can choose these 3 points as option 2, where the electric field lines always perpendicular to the equipotential surfaces. The electric field stronger when the equipotential surfaces closer to each other. And the final one, the direction of electric field lines towards the decreasing of the equipotential surfaces. For point 3, we can see how the direction of electric field lines towards the decreasing of the equipotential surfaces. We can see how the electric potential decreasing towards the direction of electric field lines from 600 volt, 500 volt, 400 volt, 300 volt, and finally 200 volt. So it is decreasing towards the direction of electric field lines. For section B, calculate the work done by the electric field on a 3 microcoulomb test charge that is displaced from point A to B for Roman 1 and A to C for Roman 2. For B Roman, work done A to B is electric potential A to B equals to work done A to B over positive test charge, which is equals to 3 microcoulomb. So we're going to substitute all the values accordingly into this formula, where VB is 200 volt, VA is 300 volt, VB is 200 volt, VA is 300 volt. We can able to get work done A to B is about -3 times 10 to power of -4 joule. We're going to use the same technique for B Roman 2. We're going to substitute all the values, possible values accordingly into this equation, where VC is 300 volt, VA is 300 volt. A and C lies on the same equipotential surface, which is 300 volt. The change of the V is 0, so that the work done from A to C is 0 joule. Simple like a bubble, without giving you any trouble. For section C, if the charge Q is 5 nanocoulomb, Roman 1, calculate the distance between the point charge Q and A. By using the formula of VA equals to KQ over RA, the electric potential for point A is 300 volt. We can substitute 300 volt at VA and substitute all the possible values accordingly in the formula to get the distance between the point Q and A is about 0.15 meter. Simple like a bubble, without giving you any trouble. Electric field at point A is equals to KQ over RA square. RA is 0.15 meter. We already got in section C1. And we're going to substitute all the possible values into this equation, a formula, to get the electric field A, which is equals to 2000 Newton per coulomb. For C Roman 3, if charge Q is 5 nanocoulomb and a new point charge of -5 nanocoulomb is placed near Q, sketch where this new charge could be placed such that the potential at A is 0. Explain your answer. We can place point A between negative charge and positive charge, where VA equals to V1 plus V2. The electric potential A is 0 for R1 equals to R2. It is because algebraic sum of V depends only on sign of charge and distance. For the last part of the questions D, if the point charge Q is replaced by a negative point charge of equal magnitude, describe the changes in the Roman 1 equipotential surfaces, Roman 2 electric field lines. For the D Roman 1 equipotential surfaces, values are negative, so all these values will be negative, no more positive. For D Roman 2, electric field lines in opposite direction or towards negative charge. Simple like a bubble, without giving you any trouble. Thank you for watching this video. Thanks a lot, and thank you to the Lord.